Today we are going to see about enhancement of transonic airfoil aerodynamics performance using the CFC approach. So this is our project. So our list of content is abstract, introduction, literature review, project cap, objective, and these and all to reference. So the abstract is this development of covalent airfoil is based on particularly we have chosen this NACA 63012 profile. By using subsonic airfoil, we are going to test and design and analysis for transonic speed. So this investigation optimizes the aerodynamic performance in transonic conditions. So by using CFD tools of ANSYS Fluent, by studying the impacts of varying jet configurations of this particular airfoil, the performance metrics include lift to drag ratio, stall behavior are evaluated and compared to baseline data. So the final results are co-flow jet significantly improves aerodynamic performance, so highlighting the potential for enhanced aircraft performance in transonic flight. So the next introduction is, so in co-flow jet airfoil concept, an injection slot near the leading edge and a suction slot near the trailing edge on the airfoil suction surface are created. So the next is small amount of mass flow is withdrawn into the airfoil near the trailing edge, and it is pressurized and energized by the pumping system inside the airfoil, and then after that injected near the leading edge in the direction tangent to the main flow. So where it creates a large vortex structures and adverse pressure gradients, which are all beneficial to enhance mixing. So CFG, by using this flow control technique like zero net mass flux active flow control technique, which is promising to achieve airfoil lift augmentation drag reduction. So particularly NACA 63012 airfoil is subsonic airfoil. We have chosen to study this in transonic regime to increase the aerodynamic performance of this subsonic airfoil. So this is our comparison between baseline airfoil and co-flow jet airfoil. So this is the injection slot location, suction slot location. So this is dimension of our CFG airfoil, where the cord length is 1000 mm and where the suction slot is located at 82% of cord, and the injection is located at 60% of cord, and the height of the injection slot is 7.5, and the height of the suction slot is 2.5 times of injection slot height. So by using these variations, by varying the location of suction injection slot, we are going to design and develop this particular airfoil by using CFG approach. So literature review. So by studying these literature surveys, we inferences that we gathered that more information about the co-flow jet in a particular transonic airfoil. So apart from this, we have chosen this subsonic airfoil to study in transonic regime. So this project, that is there is a limited analysis of co-flow jet in transonic speed, and also there is a lack of optimization of aerodynamic performance at transonic speeds in symmetrical airfoil, and also there is a lack of comparative analysis for different injection slot location. So our objective is to investigate the effect of different injection slot position by this method, and also to evaluate the changes in aerodynamic performance such as lift coefficient, drag, and pressure distribution, and also to identify the optimal injection and suction slot opening and positioning, which enhance the flow separation control and improve the overall aerodynamic performance by simulating various slot configurations by using CFD analysis tools. So research methodology is, first we have studied about co-flow jet airfoils, and we have further we have taken literature surveys, and also by studying that we have defined the problem and objectives. Then we have created the baseline CFG airfoils geometry and the CFG configurations. Finally, and testing analysis by using similar ANSYS Fluent, we have set up a simulation and run that simulation and studying the parametric. We finally concluded that results and discussions are perfectly analyzed. So this is our design of baseline airfoil. So this is our design of CFG airfoil, where the injection location slot is 10% and the next is 12% slot location. So dimensions of the above particular airfoil. So this simulation analysis of CFJ basis base of injection location 10% and also the 12%. So particularly in Mach number, shock is forming near the mid-chord at 0 angle of attack, and also pressure drops significantly followed by sudden increase. But in CFJ airfoil in Mach 0.8, shock waves near the shock waves were delayed and the pressure also increased significantly. At in Mach 1, shock waves forming near the leading edge and mid-chord were in 0 angle of attack at base, but in CFG there is an reduced shock wave formation near the leading edge and also in mid-chord, and lowest stagnation persistence recorded. So this is velocity profiles. You can see that comparison with CFG and without CFG. So the left side is without CFG and that is baseline airfoil. The right side is CFG co-flow jet airfoil. So by seeing the left velocity magnitude of counter 1, where the velocity in the upper and lower surface of the airfoil is very high, that is in red color. By comparing to the right side CFG airfoil, we can see that there is effective reduction in pressure, velocity as well as in upper and lower surface of the airfoil. So in these also velocity forming near the velocity which increases significantly by shock waves forming near the midchord in Mach 0.8 at 0 angle of attack. At every angle of attack there is a slight increase in velocity and also the pressure also. By using CFJ there is an enhanced performance in every particular angle of attack. So we have calculated among that. So we have particularly chosen that at 10% of chord where injection slot location at Mach 0.8, the CFJ airfoil has significantly improved the lift enhancement, that is, and also the aerodynamic efficiency, that is CL/CD. So these are the graphs. By comparing the CLG and base at Mach 0.8, so the left one is which is compared to CL by alpha, where they are maximum angle of attack, that is stall behavior acts at the 8 degree of angle of attack, where CL by CD ratios versus angle of attack are in the right side graph, where CFJ shows 14.39 CL by CD ratio, then base, that is 9.745. So this is CFJ versus base at Mach 1 and this is Mach 1.2. So next is simulation analysis of base versus CFJ of engine slot location at 12% of chord, as I said earlier previously. So this is comparison between CFJ and with baseline airfoil at Mach 0.8 and 0 angle of attack, and this is the velocity in 0 angle of attack at Mach 0.8. So the final results concluded that lift and drag percentage results at Mach 1 2 degree angle of attack. At Mach 1 there is a subsonic condition where the shock wave forms and turbulent flow is created in 0 angle of attack in symmetrical airfoil, but in Mach 1 2 degree angle of attack, baseline airfoil gives lift percentage 87.23%, drag is particularly that, whereas which is compared to CFG in Mach 1 2 degree angle of attack, lift percentage is 99.74 and drag is 7.28. So the CFG airfoil exhibits higher lift percentage as well as lower drag percentage compared to the base airfoil. So finally the resultant conclusion aerodynamic performance results are: in transonic regime Mach 0.8 base gives 9.74 and CFG gives 14.39. But in supersonic regime Mach 1 base gives 7.79, but CFG airfoil gives 13.700. So this demonstrates a substantial enhancement in aerodynamic performance which is compared to baseline airfoil. So this suggests that the CFG design is particularly effective in mitigating the adverse effects of shock waves and flow suppression at supersonic speeds. So conclusion: application of co-flow jet technology on this particular airfoil potentially improving the aerodynamic performance at transonic speeds by delaying the flow suppression and possibly reducing wave drag. So however, there remain several research areas that must be explored to automate CFG integration, especially for the NACA 63012. Key areas include studying the optimized configurations of transonic shortwave control. So by using CFG technology and NACA 63012, making it more viable option for transonic aircraft applications with improved efficiency and stability. So these are the references which we have studied. Among these, we have chosen particularly this airfoil to study in transonic flow.